So we were able to use Ohm's law to create a predictable voltage drop to drive a predictable voltage drop across our load for a fixed amount of current. But as we saw when we manipulated the current through our load, our voltage drop across our load changed. So this isn't a very good power supply. How can we do that better? So our issue with our previous approach is that we used a fixed 28 ohm resistor. What if we could have a resistor where we could change the value of that resistor as the load changed? So that's what we're going to do this time around. We're going to use a MOSFET, and this is a form of a transistor. MOSFET stands for metal on silicon field effect transistor, and what they're known for is being relatively efficient in that they use a voltage level to control the current through the two pins. So there's a gate, there's a drain, and a source, and the gate voltage determines how much current goes through the MOSFET. You can see this is relatively beefy. It's got a heat sink on it, a little tiny heat sink, and then you can screw this into a much larger heat sink. So this can actually take quite a lot of current through it and can switch significant amounts of amperage. It is an N-channel MOSFET, and what that means is that you have to drive the gate voltage high in order to get the MOSFET to conduct. So we've got a gate, and then we've got a drain and a sink, and if we drive that voltage high, we can get it to conduct. But that's not really what we want, and this gets into that fascinating junction between analog and digital. Typically, MOSFETs are used to digitally switch currents. So these guys turn on or off. You drive their gate voltage low, you drive their gate voltage high, they're either conducting or not. But all transistors have what's called a linear mode, where you're in the middle of that regime where they're either on or off. And this is actually the source of current draw in modern electronics. Whenever you switch a transistor, you drive it through that kind of linear mode very, very quickly, but it wastes electricity. It's not really wasting all that much electricity when it's off. It's not really wasting all that much electricity when it's on. When you switch through that linear mode between the on and the off, it's in that transition phase where this becomes a variable resistor where it starts to eat power. And we're going to take advantage of that linear mode to basically turn this into something it's not really meant to be. It's meant to be a switching device. It's meant to turn on or off, really not meant to be driven in that linear mode where it's just a variable resistor. But we can use it in that linear mode to basically replace our fixed resistor with an adaptive resistor that we can use to sink variable amounts of current through here to create a variable voltage drop across here that creates a variable voltage drop across our load that's adaptive to the amount of current that the load needs. We're going to wire that up, and after I'm done with it, I'm going to explain a little bit of the theory behind how it works. Okay, so here we have our crazy Chinese programmable load, and we've got our MOSFET over here. And because I'm going to be sinking some good amount of current through this I would not recommend this setup here. I don't have these conductors very well insulated. Yeah, this isn't great, but whatever. What I've done is I've soldered a couple wires to the various leads. This is the gate. I can never remember which is the drain and the source. I believe it's exactly opposite of what you would think it would be. So we've got the 12 volts, yes, I believe the 12 volts is the drain, and the one wired to the load, the kind of the low side, is the sink. I think that's right. If not, you'll see something on screen right now telling you it is. I also have my oscilloscope wired up here to the gate so that I can monitor the gate voltage to give an idea of what sorts of gate voltages are needed to create the voltage drop that we need to target our voltage drop across our load here. And we need to drive the gate voltage. So what we have here is a potentiometer, a variable resistor, and it has 12 volts and ground across the two outer pins of the potentiometer. So you drive this at 12 volts, that at ground. As you spin this knob, you can drive the voltage in the middle pin between 0 volts and 12 volts. Hopefully I put this back in here correctly. And we've got the gate here wired up to the middle pin of this potentiometer. So just by spinning the knob on this potentiometer, I can drive the gate voltage between 0 and 12 volts. So now I'm going to turn on my bench power supply, which is going to energize this system. And actually, I'm going to clamp my MOSFET to this ruler here, which is serving as a kind of a janky heat sink. But this is important because if I do drive significant amounts of current through here, this still, even though it's a better situation, it's a more adaptive situation, it's not a particularly efficient way of doing this. So we're still going to have the same issues that we had in the previous setup, and that we're burning off a lot of power, and that power is going to be burned off as heat, and we need a place for it to go without burning up our little MOSFET. So I'm going to turn this on, and we've got 12.997 volts across the MOSFET. And notice we're registering 0 volts right now. So we're going to start out with a gate voltage at 0. So this potentiometer is turned all the way down. And I'm going to slowly ramp it up with no load across this variable load. So I've turned the load all the way down to 0. And we're going to just see what happens to the voltage that we see across this load. Remember, we've got the MOSFET in series with our load here. So there's a voltage drop across the MOSFET, and the load sees the remainder of 12 volts minus the voltage drop across the MOSFET. So now I've got about 4 volts going into the gate, which is producing about a volt of voltage drop across the load, which means there are 11 volts of voltage drop across the MOSFET. So as I increase the gate voltage here, now I'm at about 6 volts, and I've got 2.8 volts across the load. Now I'm at 8 volts at gate voltage across this MOSFET, and I've got almost 5 volts across our load. So we're getting into the region that we want for the operation of this quote-unquote 5-volt power supply that we're trying to build with all this jank over here. You can kind of just blot that out and think of it as a 5-volt, variable 5-volt power supply. Now let's go up to 9 volts. So now we've got 9 volts of gate voltage, 9.2 volts of gate voltage, and I've got 5.76 volts across our load. So as we turn this up, we're sinking less and less voltage across the MOSFET and more voltage across our load, which means this MOSFET is starting to conduct more and more. It's becoming less of a resistance. So now I'm at 11 volts of gate voltage, and we have 7.63 volts across our load. So that means we're sinking almost 5 volts across the MOSFET and almost 8 volts across our load. So this MOSFET is starting to conduct more and more. And then I'm going to turn all the way up 12.2 volts. I don't know how we're getting 12.2 volts. And we're getting almost 9 volts across our load. So roughly 3 volts is being sunk across the MOSFET and 9 volts across our load. And this is with 0 load, so our load really isn't doing much of anything. It's sinking a very minimal amount of current, not even registerable. Now, one of the issues we're having here is this MOSFET is not fully open. If it were fully open, you would see 0 voltage across the MOSFET, and we'd see 12 volts here. But we can't get that. The gate voltage actually needs to go a couple volts higher than the drain to source voltage on the MOSFET, and we don't have that situation here. So we can only get the gate voltage up to the drain to source voltage, and that's not going to get this MOSFET into its fully conducting regime, but we don't really need it to do that because we really want it to be a variable resistor. We don't want it to be full on, and we don't want it to be full off. So that doesn't really matter for our purposes here. Now what I'm going to do is I'm going to dial up our 250 milliamp load. You notice immediately as I increase the load, the voltage drops a little bit. So I'm close to my 250 milliamp load within the accuracy of this crazy little device. So you can see that we've got too high of a voltage here. So what we're going to do is we're going to decrease the gate voltage until we get down into our 5 volt, until we get down to the 5 volts that we want to target for this particular. That's close enough within the accuracy of this device. So 4.93 volts, roughly 5 volts. And to achieve that, what we have is 9 volts of gate voltage. So we are really in that middle regime of the MOSFET. Typically you want to provide 0 or something like 13 or 14 volts to turn it on or off. We're in that middle there. We're driving the MOSFET in its linear regime. It's dropping 7 volts and we're seeing 5 volts across our load at 0.25 amps or 250 milliamps. And if we wanted to calculate what the resistance of the MOSFET is right now, we can do that using Ohm's law. So it is, the voltage, which is 7 volts, equals the current, which is 0.25 amps, times the resistance. So if we do the math, we get that the resistance is 4 times 7 equals 28, which is what we had originally, right? So now we basically duplicated these guys that were a fixed resistance with the variable resistance of the MOSFET. But here's the cool part. If I adjust this load, so if I turn the load way down, say I turn down the volume on my radio and I'm not using nearly as much to produce the amplified output, you see the voltage across our load goes up. So to adapt to that, we need to turn down the gate voltage a little bit more. Oh, that was perfect. To target the 5 volts that we want across this load. So we've got effectively a very janky, adaptable 5 volt power supply, but you can't imagine anybody really using this. Like if I turn the load way up here, let's get these little guys spinning, you can see the voltage drops. So that means I need to turn the gate voltage up to compensate to get that voltage back up into the range that we're looking at. So now we're sinking 500 milliamps across this load, but we've still been able to maintain that, but our gate voltage is at 9.2 volts. We can go even higher. So now we're sinking 750 milliamps across here, but the entire setup is taking about 9 watts of power. One of the other things that we're going to notice about this is that very small changes in gate voltage result in large changes in the conductivity of the MOSFET. So when I go down to almost, a very, very low amperage rate here, in order to target my 5 volts, I've got 8.72 volts across the gate. Now, if I turn this way up, let's put it 710 milliamps, and I get this back up to my 5 volts here. I've got 9.2 volts. So that's a relatively small change in gate voltage, resulting in a significant difference in the amperage across our load. So this potentiometer setup here is highly sensitive to the gate voltage. So very, very small changes in gate voltage can drive large changes in the voltage and the current through our load. So this is kind of a sensitive fiddly system. Like you would never want to use this in real life. Now we've been running quite a lot of current through here for a little bit, and we've been running about 9 watts through our entire system. And yes, indeed, this little ruler here is getting quite warm to the touch, and the MOSFET itself is, ow, yeah, that hurt. So I'm gonna turn this back down. I haven't burned out a MOSFET yet, but you know, there's a first time for anything. So with this setup, we've created an adaptive 5-volt power supply that we can adjust to the current draw of our crazy little load here. But it's not really realistic. So what I'm going to talk about next is a little bit of the theory behind how this works and what we can do to more adaptively control the gate voltage of this MOSFET to produce something that's called a linear regulator, sometimes called an LDO. So we're going to create our own little linear regulator, but that'll be in the next video. So let's go over what we just did. We made a simple circuit with a battery or a power source that goes to a variable resistor. Here's a symbol for the variable resistor. It has a tap kind of in the middle here, which kind of rides along this resistor, and you bias the variable resistor with 12 volts on one side and ground on the other. And so as you move this variable resistor up and down, this guy like that, you can make this terminal, the center terminal, go between 12 volts and 0 volts or ground. And then we wired this center tap up to the gate on a transistor. And I'm probably going to butcher this symbol for a transistor. There we go. Something like that. So we were able to drive the gate from this variable resistor, 12 volts, that puts this into the linear conducting mode. So what that means is that the resistance of the MOSFET is proportional to the gate voltage. So what we could do with that is that if we put our load in here in series with this, we can target a particular voltage drop across our 0.25 amp load. And we saw, there's our MOSFET. We can dial in a particular voltage drop across our MOSFET to target our 5-volt voltage drop across our load here. And we hooked this up and it actually worked. We were able to it was very, very fiddly. We were able to just dial in the right amount of resistance on this MOSFET in linear mode to get the right voltage drop, about 7 volts, to give us the 5-volt voltage drop across our load, which is exactly what we wanted. Then we saw as we changed the current of our load, the voltage across our load varied dramatically. And you could adjust by adjusting this little potentiometer, but that's a very fiddly way of doing things. What would happen if instead we replaced the potentiometer with a microcontroller? So this is a Raspberry Pi Pico. It's probably overkill for our purposes here, but it can effectively sense the voltage across this load and adjust the gate voltage here. So what we can do is we can have it sense this voltage on one pin, and we can have it adjust the voltage of the gate using another pin. It's a bit more complicated than that, but we can get it to work in this way. We can have something that dynamically at the millisecond level does the equivalent of what we were doing twiddling this potentiometer. We can have this do that at the millisecond level to always target having 5 volts across our load by dynamically adjusting the gate voltage of this MOSFET. So that's what we're going to do next. So that's what we're going to do in the next video. We're going to use a microcontroller to control our MOSFET in its linear mode to create an adaptable variable resistor that effectively very tightly controls the voltage across our load even as that load changes and adapts in real time. And this is essentially what linear regulators do. Linear regulators are a very popular component in electronics. They have all of this circuitry built into them. They are much cheaper than using a microcontroller to do it, but I think it's a little bit more instructive to actually understand what's going on inside these things and some of the mechanisms of control that can be used to adaptively sense the voltage across your load and change the gate voltage in such a way that you don't overshoot or undershoot, and that you have very, very tight control for your power supply.